Hello, this is Mr. Manley. In this video I'm going to look at how to solve a linear programming problem. In a linear programming problem, we have a situation where there are limitations placed upon us, and we want to find out within those limitations what is the optimal outcome. So why don't you just take a moment and hit pause and read this problem for the given week, Kareem's Coffee House. Okay, welcome back. And so what have we got here? Hopefully you can get to the bottom line here pretty quick, which is that the profit, what we were interested in is profit, and the profit is going to be equal to 3 times E, that's however many bags of the economy blend we sell, plus 4 times P, that's the number of packages of the premium blend that we sell. So the question is, how many packages of each are we going to sell? If I were to look at the, just like say, let's just say I was going to do, I thought I wanted to do 100 of the economy, and I wanted to do make 100 bags of the premium blend. So let's just say that that's what I wanted to do. What would that mean for us? If we look at the economy blend, it's going to use 2 ounces. That just blocks it out. Let me see if I can find a highlighter here. Okay, so that is that's going to be 2 ounces of the grade A and 10 ounces of the grade B for each bag. So that would mean that I would be using 200 ounces of A and 10 times 100, 1,000 ounces of B. And then if I look at the premium blend, we would find that I would be using, let's see, where is it? 9 ounces of grade A, of the grade A. So if I do 100 bags, that's going to be 900 ounces, and then 2 ounces per bag of grade B. So it's going to be 200 ounces. These are all ounces here, OZ. So 200 ounces of that. And then, so what would that mean? In order to do this, in order to make 100 bags of economy and 100 bags of premium, I would be using, and I forgot to mark these off here. Let's see, this is 900 ounces of A and 200 of B, right? Okay, so that would mean that I would be using 1,200 ounces of the grade A coffee and 1,200 ounces, or 1,100 ounces of the grade A and 1,200 ounces of the grade B. Now look up here, and I have 1,700, 28, 76. So I didn't use all of the coffee in this scenario, but I would just want to throw it out there that this is what somebody could do. They could say, oh, I think I can make 100 bags and 100 bags, and then what would that entail? And then I can look at how much profit would I get out of that if I could sell all of those 100 bags. So that's what's kind of going on, right? But we want to mathematize things. We want to use some mathematics here to really optimize, well, how many bags of each kind should we make? And this is what linear programming does. Now, if you've watched an introductory video on linear programming, you know that the first thing that we want to do is find the objective, what is called the objective function, which is often the profit, which is often going to be a profit function, not always. So we've got that here. We've got the objective function. So know that word. I'm just going to write it down just so you're hearing, you know what you're hearing. Objective function. Okay, and that's the profit equation. Okay? Now the next thing that we want to do is find the constraints. And the constraints are the inequalities that are based upon the limits of our situation. So in this situation, so let's look for what is constraining us. We know that when we make this economy blend here, we are using 2 ounces of A and 10 ounces of B. So for the economy blend, which is this E here, that's the number of bags of the economy blend is E, and P is the number of bags of the premium blend. So for each bag of the economy blend, I am getting 2 times E is how much grade A. 2 ounces per bag is how much of the grade A that I'm using in the economy blend. Plus, for the premium blend, how much am I doing? I'm using 9 ounces of grade A each time I make a premium, and my total grade A available is 1728. So this has to be less than or equal to 1728. Let's take a look and make sure that you follow that. So I'm looking at, this is like the grade, this is the equation for the grade A coffee. This equation here is for grade A. And then it's not an equation, it's an inequality. And then I'm going to do an inequality for grade B, and you should be working on that in your mind already now that you understand how things are developing here. So in the next case, I've got the 10 ounces of grade B in the economy blend. So that's going to be 10 ounces for each bag of E. Plus in the premium blend, I'm doing 2 ounces for each bag of the premium blend, and I have a total of 1760 available. So that's got to be less than 1,760. And that's my grade B equation. Is there anything else that is limiting me here? I don't think so. I'm not seeing anything else that would place any limits on me in this problem. All right, so now we've got our constraints, we've got our objective function. Now we want to find the feasible region, and that simply means solve the inequality, solve the system of inequalities. So let me give myself some space here, and okay, I'm going to try and graph this on this page. Hopefully I have enough space. And so I've set up an XY axis, but in this case it's an EP axis, right? So the my economy blend E is going to be the horizontal axis, and my premium blend P is going to be the vertical axis. With that, I'm going to graph these two equations. I'm going to go ahead and I'm not going to work through the process of graphing. I presume that you know how to graph and how to determine what scale you should use on your two axes. Okay, so basically what I've done here is I've graphed the inequalities. Notice a couple of things. One is I number my inequalities, and I number them where they're written, and then I'm able to number them on the graph so that I'm going to be able to keep track of where I am with things. Here I just looked for the X and Y intercepts, and then I've got them graphed, and of course we are less than or equal to on both of these, so both of these are going to be looking this way down, and then the place where they're going to overlap is going to be down here in this little corner that includes the origin down there. Okay, now the next thing that we need to do, so that now this is this little piece down here that is the solution to the system is the feasible This is the feasible region. So remember at the beginning I just said, well, let's say we're going to do 100 of the economy and 100 of the premium. Well, that number is in here. That number is in the feasible region. You'll remember that we still had some grade A coffee left over and some grade B coffee left over because we didn't use it all. What we are looking for is we want to know what point in this feasible region, and let me expand it here and just I'm just taking this feasible region that is down there and just expanding it up here. All right, so there's the feasible region, and the 100 that I did at the beginning, which was just a guess, where's that going to be? That's going to be like here. That's going to be like in there. So it is in the feasible region. Now, if I chose something else, if I said something like, let's make 200 of, or let's make 300 of E and 300. Well, that would be up here. So there would be 300 there, and that's not in the feasible region. And the reason that it is not in the feasible region is because I don't have enough coffee. I'm going to run out of coffee if I try to do that. What our job is here is to find out within this feasible region, where is the point? And if you look at where I pulled it out up here, this bigger one here, the question is, where's the point in here that will give me the maximum profit is what we're going for. What linear programming tells us is that the maximum profit is going to be here, here, or here. Technically, I would say there. I know it's not going to be there, but that technically is another what is called corner point. So this is the other piece of a linear program. We have the objective function, we have the constraints, we have the feasible region, and now we have the corner points. So if I number these corner points, letter them A, B, C, D, what I want to do next is I want to find these corner points. All right, so let me go ahead and erase this guy here, and then we'll go about finding the work for the corner points. Okay, so looking down, I'm gonna label them down here. I'm gonna call that A. So corner point A is obviously 0, 0. And then look there, I'm going to call that corner point B, and you must label them on the graph. And corner point B is obviously 0, 192, right? You can tell that from the graph and from my table of values. And then I'm going to call this corner point C. That one we're going to need to find. It's going to be the intersection between 1 and 2. And then down here we have corner point D. And corner point D is going to be obviously 176.0. We can tell that from our graph and our table of values. So I'm going to go up here and say that I'm going to find C. Now understand, I'm a little bit constrained here by the space, my space on Doceri, so you wouldn't want to feel obligated to crush everything in here. Okay, but I think I can fit it and do it fairly neatly, so I don't have to go to another page. All right, so I'm going to find C. That's going to be the intersection of 1 and 2. All right, so what am I going to do? I'm going to multiply number 1 by 5, so that'll give me 10E plus 45P is equal to 8640. And then I've got 10E plus 2P is equal to 1760, and I'm going to subtract those. So that'll leave me with 43P equal to 6880, and then P would be equal to 160. All right, now it would be good at this point to stop and look and see, does that make sense based upon my graph. So if I look at C here and I look at my graph scale, does P equals 160? That'd be the vertical scale for P. Does P equals 160 make sense? And yeah, it does. I don't have a really accurate graph here necessarily, but yeah, I mean, it definitely looks like 160 is possible. And then having found the 160, I can substitute that back in, and I can find the value of E, right? Should be easy enough to do that. Okay, so I'm getting E is 144, and that'll close out our calculations for C over here. So that's 144 for the E, and then give myself a little more space here, and 160 for the P. So those are our corner points, and now remember I said which the optimal situation, in this case the maximum profit, is at one of these corner points. Okay, we can obviously throw out A, so it's not happening at A. Now I'm gonna calculate the others. I'm gonna go P, B. So this is going to be the profit at B, and that is going to be so I'm using this this B here, and that's, so I'm doing 0 of bag E and then 192 of bag P. So that's just going to be the profit is going to be equal to 4 times 192. And that is 768. So if I chose this option B, and I made 0 of the economy brand and 192 of the premium brand, my profit would be $768. Then I'm going to show P. I'm going to show PD actually first. So PD, that's going to be 176 of the economy brand, and I get $3 for each bag of economy brand I sell. So that's 3 times 176. That's clearly going to be less than PB, right? Because this number is less than that number, and this number is less than that number. So it's clearly going to be less. I'll go ahead and do the calculation anyway. So $528 if I just make 176 of the economy blend. Now I'm going to go PC, and PC I'm going to make $3 for each economy, and that's 144. If I look over at corner point C, that says I should do 144 of the economy blend, and then I'm going to get $4. That's going to be plus $4 for each of the premium blend that I make, and if I use corner point C, I'm going to do 160 bags of that. So let's go here and calculate that. And we get, as expected, 1,072 is the greatest profit that we can make. And we would answer the question by saying, so just recall the question is how many packages of each blend should we make to maximize profit? Okay, so I'm going to just give myself a little space down here and say that the answer that we want is 144 economy blend and 160 of the premium blend, and that is our response to the question. I just want to make a couple of more comments here. One is that you might be tempted to think that corner point C is obvious, and a lot of times corner point C, when you have a feasible region that looks like this, and if the feasible region looks like the one that we had, a lot of times the feasible or the corner point that is here that is there. That is a lot of times where the optimal situation is. But that's not always the case. So you do need to check. That's one thing. The other thing is that this looks like a lot. There's a lot on the page here, right? But notice everything is labeled. Everything is labeled and well ordered. So even though it looks like a lot of information on the page, we can follow it if you do everything with the labels. And it might look a little bit like a lot of information, but it should be very readable. So use these labels and show all of the work, all of the calculations. Do things like this. If you look down at my corner points here, do things like include A. It just completes the picture. We know that it's not going to be A, but we include it anyway. We do all of these calculations. If you look over to the right, I'm going to do PD just to complete the picture, just so nothing's missing and we don't have any question or any doubt. Okay. All right. So that is linear programming, and definitely going to need to practice a couple of those or do a couple of those. And a big issue is going to be, are you showing your work and are you showing it clearly? You do need to do that. You do need to follow the process and do need to show your work clearly on these problems if you have a submission for it.